By analyzing different methods of propulsion in the air, such as the flapping of a bird, the blades of a helicopter, the turbines of an airplane, or even the takeoff of a rocket, we will realize that they all work thanks to the same fundamental principle of physics. When a force is exerted on an object, a force of equal intensity but opposite direction is exerted on the object that produced it. This is better known as Newton's third law, or the principle of action and reaction. Understanding this, there is a technology that takes this concept to the extreme, reducing the amount of propellant but ejecting it at speeds of even hundreds of kilometers per second. I am talking about electric propulsion systems, of which there are several types, the most widely used today being ion thrusters and Hall thrusters. In simple terms, they use electric fields to accelerate atoms and eject them at high speeds. But obviously there is much more to it. So in this video we will look at how an ion thruster works, in addition to its benefits, limitations, and uses. To understand how an ion thruster works, we must first understand how atoms are composed, what an ion is, and what plasma is. An atom in simple terms is composed mainly of three subatomic particles. Neutrons, which have a high mass, but no electric charge. Protons, also of high mass but with a positive charge. And electrons, with a low mass and a charge of equal value to that of the proton, but negative. In this case, when I say high or low mass I mean in relative terms, with electrons having a mass about 1,800 times smaller than protons or neutrons. Understanding this, the atoms of different elements are composed of different amounts of these particles, and as long as the amount of protons is equal to the amount of electrons, the charges cancel out and the atom will have a neutral charge. On the other hand, if there are more electrons than protons, the atom will have a negative charge, and if there are more protons than electrons, the atom will have a positive charge. These two cases are what is known as an ion. Under normal conditions, if we had a liquid or a gas with a mixture of ions with different charges, they would interact with each other, attracting each other if they have electric charges of opposite signs, forming in this process new molecules with different properties. Similar to what we saw in the video on how batteries work. But all this behavior changes slightly when the ions are in a state of matter known as plasma, in which the ions and electrons will remain separated, which also allows them to act as electrical conductors. Although it is important to mention that, for this to happen, some conditions must usually be met, such as high temperatures, strong electromagnetic fields, or the presence of microwaves. Getting that out of the way, let's look at how to build an ion thruster and the effect each of its components has. The first element we will need is a container with an open end and a closed end. To this we will add an inlet at the closed end, through which we will introduce a gas such as xenon, which is a noble gas. That is to say that in normal conditions it is presented as individual atoms with neutral charge, which does not react easily with other elements, and therefore facilitates the handling and storage. But more important than that, it is an element with a high atomic mass, which, as we will see later, is extremely important for the operation of the propellant. At this point, if we let the xenon in, nothing will happen, it will simply disperse and come out of the open end of the container. The next element we will add will be an electron gun, also known as a hollow cathode. This consists of a tube with a hole, which inside has a material such as tungsten covered with barium oxide, which is also surrounded by a resistor. The principle of its operation is that by heating the resistance, this will heat the material inside, which by a phenomenon known as thermionic emission will begin to emit electrons, similar to how vacuum diodes work. A small amount of xenon is then injected into the tube from the rear. Having a small volume at high temperature with electrons being continuously emitted generates the correct environment for plasma to be created. More specifically, the electrons collide with the xenon atoms, which, let's remember, had a neutral charge and caused them to lose one of their electrons, becoming now positively charged xenon ions. Now we will have a plasma volume composed mostly of electrons, and since xenon continues to be injected from the rear, it will be forced out through the hole. Furthermore, to aid this process, a positively charged cover is added, which has a dual function. Firstly, it guides the electrons into the orifice, and secondly, it prevents other particles from entering the section where the plasma is generated and affecting its operation. If we reanalyze the components we have so far and inject xenon into the main container at the same time we use the electron gun, the behavior will be repeated, but this time on a larger scale. Again, the electrons collide with the neutral xenon. They will remove one of its electrons and convert it into positive ions, generating plasma. However, this time the conditions will be different in terms of pressure, temperature, and magnetic fields present, which is why the ionization of the xenon will not be very efficient. To overcome this, a series of magnetic rings are added around the main container, which increase the efficiency of ionization and help contain the generated plasma. Having a continuous source of large amounts of plasma, we can finally start talking about how the propulsion is generated. For this purpose, a double grid is added to the open end of the container, each of them electrically charged due to the application of high voltages. The inner one is positively charged, and the outer one, negatively charged. Since plasma is continuously being generated, the pressure inside the container will be increasing, and since these grids are the only way out, both electrons and xenon ions will try to pass through them. If we analyze the behavior of an electron, it will be attracted to the positively charged inner grid, and may even pass through due to the pressure inside the container. But since the second grid is negative, the electron will be repelled, pushing it back into the container. On the contrary, if we analyze the behavior of xenon, it will be repelled by the first grid. But if we consider that it is being pushed by the pressure of the plasma in the container and it gets through the first grid, it will automatically be repelled in the opposite direction. And not only that, it will also be attracted by the second negatively charged grid, accelerating the xenon ions to enormous speeds, in the order of tens or even hundreds of kilometers per second depending on the voltages used. To give you a point of reference, the speed at which the gases are ejected in a rocket is only about 3 kilometers per second. Returning now to Newton's third law that I mentioned at the beginning of the video, the principle of action and reaction, we will know that the forward thrust will be equal to the force applied on the xenon ions to accelerate them to those velocities. Furthermore, if we consider Newton's second law, which tells us that force equals mass times acceleration, we will realize why the use of gases such as xenon is preferred, because by having a relatively high atomic mass we are maximizing the two variables that affect the thrust force. At this point it would appear that we have a fully functional ion thruster, but the truth is that we still have a small problem. While the xenon is being accelerated when it is between the two grids, once it passes through the second grid will begin to attract it in the opposite direction, partially neutralizing its effectiveness. Or xenon ions could even be diverted to other parts of the satellite that might be electrically charged and potentially interfere with its operation. Luckily, the solution is quite simple. The last element needed in an ion thruster is a second electron gun on the outside, which is responsible for returning the xenon ions to a neutral charge. And since the electrons have a much smaller mass than the xenon atoms, their effect on the speed at which they are ejected is minimal. Now that we know how an ion thruster works and that they are capable of ejecting gases at much higher velocities than other conventional methods, I have to tell you some sad news. The propulsive forces they are capable of generating are much lower than other methods. On Earth, an ion thruster like this would not even be able to lift its own weight. But that doesn't mean it's not useful, since traditional methods also have their limitations. A rocket can generate a great deal of propulsive force, but only for a few minutes. Besides, much of that propulsive force is used to accelerate the huge amounts of propellant needed, and not the main charge. In contrast, ion thrusters can generate relatively small forces but keep running for months or even years with a much smaller amount of propellant. And for this reason they are ideal for adjusting the trajectory of probes and satellites, or even powering long-duration space missions, allowing much higher final velocities to be achieved. Oh, and in case you were wondering, although this seems a completely futuristic technology, the truth is that ion thrusters have been used for more than 50 years. Although, of course, they have undergone multiple evolutions that have increased their efficiency and propulsive force generated. If you are interested in space technology, I recommend you to watch my video about how the nuclear batteries that have kept the Voyager probes working for more than 40 years work. I hope you liked this video. Remember to subscribe and support me on Patreon if you think what I do is worth it. That's all for now and see you in the next video.